Okay, how's the manufacturing industry responded to the Anthropocene epoch so far? Extensive innovation and investment on more sustainable production methods, recycling of waste oil from water vehicles, construction equipment, power generation, ships, fishing boats, and transmission and reuses it as fuel to high energy processes, and reduction of greenhouse gas emissions intensity by 2% last year. Some further responses to the Anthropocene epoch: using co-products or waste products as a substitute raw material, firms are investigating various co-products that can be used to reduce the carbon footprint of a finished product. An example here is to use GGBS in concrete for harsh environments so that high quantities of cement are not required. Electricity being generated from the production processes, harvesting of heat energy, solar energy and wind energy to help run the operational process again. The key example here is solar and wind energy being generated from a production plant to help run the next key phase of production. And finally, water recycling. Water recycling: almost all production processes require water usage. This water can then be recycled back through the system numerous times before it is disposed of in an environmentally friendly manner, e.g., steel fabrication. The aim as a nation is to have a new water usage of 0. What else can be done? Further collaboration with research institutes, perhaps partnering up with research institutes or leading universities to carry out research on more efficient ways of doing something. Increased rate of energy harvesting from industrial equipment. We can increase the amount of solar, wind or heat energy being harvested from the production process. This can be used to aim for the net energy usage of 0. Enhance safety precautions and training for workers to enable food protection while in the workplace. So further training and incentives to employers to promote a safer and healthier work environment is the key to a more sustainable and restorative work environment. Employ partnerships with local firms to use waste material as an energy source. Waste material from the production and construction processes used at industry plants to generate energy for the production process. This is commonly done at cement production plants, where waste needles are taken from hospitals and used to generate energy by burning them in the furnace. Number 5, examine alternative sources of transport for finished product, i.e. train, barge, boat, etc. The most common method of delivery is by truck. If a site is in a suitable location, or if long draws are required, look at alternative options that can be used. Designing for sustainability. What are the various ways the applied action can be resisted? We're going to have a look at some typical structural engineering examples to start off with. First of all, we have a bridge project. Next, a clear span structure, a transfer structure, a column design, and finally a steel connection design. So, taking a closer look at these examples, bridge project. If we have a 300-meter span, a suspension bridge would be more suitable than, say, a tied arch or catenary bridge. If we start with a tied arch bridge, how sustainable do you think it will be in regards to the structural efficiency, material usage, deflections, etc.? Now, looking at clear spans. For a 50-meter open span inside a building, what do we need to consider? If it is a warehouse, it does not need to be pretty, and to enclose a portal frame usually just is to meet specification. What about an airport? A portal frame or space frame may not be acceptable. Perhaps a space frame may be more acceptable though than a portal frame. We need to make sure that people feel comfort and welcomed by inviting them into a sustainable restorative development. Number 3, extremely large actions on columns. What are the most common options? A. We can use pure reinforced concrete columns, which will be large clunky sections that will take up a lot of space. Construction issues that will arise are differential heating leading to cracking, and finally very large quantities of cement will be required, increasing the carbon footprint of the development, etc. As an alternative, we can use peel steel columns, which generally require a specialized steel grade, such as 460 NNL. Some production issues that may arise are the fabrication of very thick plates, requiring preheating of plates to allow fusing of the plates during the welding process. S460N cost approximately 50% more than the standard grades of steel used in this country. The carbon footprint is very high, not just for the manufacturing process alone due to the extremely large amount of energy that is required. C. Finally, we can use composite columns, which involve standard steel columns embedded in a standard concrete grade. There are shear studs welded to the columns using a Hilti welding gun, which allow composite action between the steel and the concrete. Much smaller sections are achieved, reduce carbon emissions from production and construction phase, and the level of contractual work required to complete is of a common standard throughout the world. From an engineering and climate action point of view, which option would you think would be most suitable? Possibly the composite construction. The next one is the transfer structure. Critical factors to consider with transfer structures are: where is the structural system located in the building, i.e. edge of building or centre of building? Taking a hotel lobby as our example, do you think it would be more suitable for a 2.5 metre transfer fuse truss to be loaded in the floor above, or a 1.2 deep reinforced concrete beam? If the solution is not practical, it's certainly not sustainable. If it was on the edge of a building, a truss would be a more suitable option over one floor and would not cause any intrusions inside the building. Number 5, connections. Structural connections in a building, for example a steel building. Following on from point 3, pure steel columns to resist over 110 meganewtons will be approximately 5,500 kilograms per meter run. If I used a thin plate connection for the floor beams, I will require a 8 to 15 millimeter thick cleat plate to be welded to the column flange. How easily do you think this plate can be damaged on a column while being maneuvered, transported or erected? In this scenario, an end plate connection would be the most suitable connection type, with no plates being required to be welded to the column flange, eliminating the possibility of damaging the plate, which will improve the program reliability. And finally, we have design competency. If you have not completed a design process before, you need to have some training and guidance before, during the task. All calculations must be checked by an experienced engineer. So, fundamentals of engineering to approximate section size. In any conceptual design, it's essential for us to have a strong foundation in our structural mechanics. It could be treated as the foundation for starting any sustainably sized section. For example, there's no need to use an 800mm deep reinforced concrete beam if all we need is a 500mm deep beam. This 500mm deep starting point can be easily extracted from your mechanics calculations. The fundamentals of engineering should be used for sizing all structural elements at the initial design stage, and it provides a foundation of understanding to why exactly the chosen size has been selected. Speak and review as you go. A quick example has been included here to size a steel beam, and this should be told as a story. As you can see here, the story is using these equations, you're able to get a very quick idea as to the size. More commonly, what's used in design offices are span to depth ratios. These require less work and less understanding, possibly an unfavorable approach. We need to have a good understanding of the fundamentals of engineering to understand the boundaries within we work. So the second example is the typical truss with a point load applied to it. Bending resistance is treated as a push-pull or couple resisting the bending action. The tension and compression resist the bending moment though through the couple force action, therefore C equals T. Now we can pick out a suitable section from the section tables to start with. Buckling capacity will be critical. Similarly for diagonals, they act as the web in the truss by resisting the shear action. Critical force can be found in the diagonal closest to the support. Method of joints can be used to find this. The next phase of the life cycle assessment that we're going to discuss is the building part manufacturing stage. With the building materials we have produced, how can we use these materials to make construction parts? Taking some building parts examples, first of all we have precast concrete products, next we have steel fabrication in the workshop, next we have glulam timber beam production, next we have structural glass production, and finally we've got the production of PCV draining pipes. Factors to consider when looking at the fabrication process. Our first factor is the manufacturing resources available to us for the parts required. Next, the environmental impact that the fabrication process in question poses. 3. The cost of production process must be considered, and this be influenced by how well equipped we are to produce the building parts. Next is the logistical capabilities we have available to transport the building parts. An example of this is transporting an 80-meter glulam beam. Do we have the resources to deliver this scale of the element? And finally, we need to consider the labour skill set available to us. Continuing on from the last point, have we the skilled labourers available to manufacture the beam? So let's take a look at sustainable structural timber, which I know that Gary has talked more about. Advantages: it's got a high strength capacity, delivers nature-themed development, raw materials, local and renewable, low energy consumption for part manufacturing process, absorbs carbon dioxide, and maintenance over life cycle will depend on productive coating applied. The disadvantages: fire regulations are a major obstacle, manufacturing processes are very specialized, structural parts can be easily damaged, connection design can be complex, activities could lead to timber supplies, activists could lead to timber supply shortages, and design competency. So, about cross-laminated timber, this picture shows the bracing connection, and when examining closer detail you can see the complexity of the connection, various methods of the connection for the glulam. The top picture shows the glulam runner beams providing a clear open span space for a swimming pool, and there is a video that you can watch, and this shows the glulam or cross-laminated timber manufacturing process and the equipment that is required to produce such parts. What about precast manufacturing? Advantages: excellent quality control, exact material quantities coming from BIM, less environmental pollution on site when pouring the concrete, quick installation process, low maintenance over life cycle for fair-faced, and efficient structural systems means a reduction in section size. The disadvantages: robustness in high-rise buildings still being researched in many institutes, manufacturing process is specialized, connection design is complex, emissions required to produce the finished product are higher than the timber, design competency for precast, and educational process involved around RC. The picture on the left shows the formwork for the wall panels ready to be poured in the factory. The top picture shows the completed floor slabs being lifted out onto the loading bay, and finally the video provides a demonstration of the precast manufacturing process and the equipment that is required to form some wall panel parts. The next phase of a development, life cycle and assessment is the assembly of the parts or the construction process for the built environment. Some common construction processes on site. The first is traditional in situ construction. Next we have prefabricated steel framing. Next we have precast construction. And last but not least we have modular pod construction. Choosing a sustainable construction method. The construction method is becoming a more dominant factor for when a client is aiming for sustainable and/or living accredited development. Factors to consider when selecting a construction method: carbon footprint strategy, environmental protection policy, quality assurance target, complexity of development, labour resources, program schedule, and site location. So let's take a look at the traditional construction method, or in situ construction. Firstly, release of carbon emissions. The cement production accounts for 8% of carbon released on an annual basis. Other factors to consider: the transportation emissions for large quantities of concrete, i.e. 200 to 300 trucks in one day. 2. Imperfections in the structure constructed. It is next to impossible to construct the building we design in detail in a 3D structural engineering software. However, as the physical imperfections become greater, internal or secondary stresses can be introduced at key locations that have not been accounted for. This leads to a structure that is not behaving as expected, which is a major issue. This phenomenon can lead to deflection issues, spalling, cracking of concrete, life cycle issues, etc. Number 3. When estimating the quantity of concrete required for a large floor slab, it is common practice to spend more concrete than you need rather than running short. This amount varies depending on the risk factor and the importance of the finish to the element, i.e. exposed concrete wall in a prestigious office block versus a farmyard wall. Therefore, there's almost always concrete over that needs to be disposed of. The method of disposal can vary greatly depending on the site, i.e. a small country site can typically dump it in an environmentally friendly manner. Number 4. High labour demands on site. Reinforced concrete usually requires at least 4 crews on one team: carpenters, steel fixers, concrete pourers, curers. For any city centre site, this can lead to 1,000 to 2,000 workers on site. This high level of staff on site requires the health and safety risk on any site with more people and moving parts in a confined space. Number 5. Logistics of busy city centre sites. For large concrete pours in a busy city centre site, it is common to have 100 to 200 concrete delivery trucks coming to site in any one day. Factors that we need to consider are: will the surrounding buildings accept these trucks, e.g. a prestigious hotel? You might have schools with a lot of pedestrians or government buildings with a Grada station that will not want the roads blocked up with delivery trucks. And number 6. Concrete strength delays. Usually tests are carried out at 7, 14 and 21 days, and may slightly vary depending on location. If the target strength is not met on day 7, works must be delayed until the next test date to ensure the specified capabilities are met to allow work to commence. This causes a lot of uncertainty in the programming of the development, which is not favourable in the modern construction world. So, some tips on how to protect the environment while pouring concrete. Concrete is extremely toxic to the environment, and it takes 100,000 litres of water to dilute 1 litre of concrete. It is essential to keep the site clean and tidy with no excess water around the site where the pouring of concrete is being carried out. More recent construction methods. This time we're going to be looking at steel and concrete framing. Since the building is mainly manufactured in the workshop, better accuracy can be achieved as it is assembled on site in accordance with the workshop drawings. If something is wrong, it is a lot easier to find the fault and who is to blame for the problem. Imperfections can also be more accurately modelled to include additional stresses that may be caused due to imperfections, e.g. applying an action at a specified eccentricity for the connection type used in the structural system. Less waste is generated. Since the production of the building is carried out in a factory environment, more stringent measuring techniques are in place to ensure as little waste as possible is achieved. On an industry level for the likes of structural steel, all members are cut using a CNC machine to the nearest dimension, i.e. the nearest millimetre, but can depend on the equipment resourcing. If there are offcuts from the raw steel, they are collected into an allocated section and either reused for smaller details, e.g. complex connections, haunches, etc., or are sent back to the raw material producer to be recycled into new products. Reduce noise and dust production. Number 3. On-site compared to in-situ construction. Large amounts of vehicles coming to and from the site leads to an unfriendly environment for the surrounding buildings, i.e. dust, dirt on the roadways, danger to pedestrians, etc. By using prefabricated sections, more stringent control can be kept on the environmental impact to the surrounding areas. A drop and collect system is a typical method that is carried out with articulated trailers to reduce the transport emissions during the construction phase. Number 4. Suitable to a city centre site. Taking a large concrete pour as an example, if trucks get delayed due to traffic congestion, concrete will begin to set in the truck and may require some retarding agent, concrete additive. By using prefabricated elements, it is not as significant if the truck gets delayed where the elements are already formed in the factory. Number 5. Lower labour demands for prefabricated structural solutions. Generally, the crews on site are working for the specified contractor, e.g. steel erector with steel fabricator or precast installer for the precast fabricator. Since these workers are specialised and have intensive experiences, safety is greatly enhanced on site, adding to the sustainability of the solution. With accidents comes fatalities, and with fatalities come major cost and negative publicity to the firm in question. And number 6. Almost full strength is achieved after the installation of the prefabricated members. This enables rapid progression of the development on the schedule initially programmed. Clients looking for rapid build tend to prefer this option as there is more certainty in the program schedule. Now moving on to precast concrete buildings, precast construction. Firstly, excellent quality control. The entire building is manufactured in the workshop. This means imperfections can be usually found during the inspection process before leaving the workshop. Better finish to the concrete is also a major factor as to why this option is chosen if the concrete is being left exposed, i.e. fair-faced concrete. Almost zero waste as the development is manufactured into full-size pieces in a factory environment. Any material that is left over from one structural section can be recycled and used in another section. This reduces the carbon footprint over the development, immensely improving the green building status of the development. Number 3. Reduced noise and dust pollution on site compared to in-situ construction. Large amounts of vehicles coming to from site cause an environmental impact to the surrounding area, i.e. dust, dirt on roadways, danger to pedestrians, etc. Using this construction method is much more suitable to help protect the surrounding areas from these major obstacles. Number 4. Logistics. Suitable for a city centre site. By using this method over in-situ construction, it is not as significant if the truck gets delayed where elements are already formed in the factory. Number 5. Lower labour demands for prefabricated structural systems. Generally, the crews on site are working for the specified contractor, i.e. precast installer for precast fabricator. Since these workers are specialised and have intensive experience, safety is greatly enhanced on site, adding to the sustainability of the solution. With accidents come fatalities, and with fatalities come major cost and negative publicity to the firm in question. And number 6. Almost full strength is achieved after installation of the prefabricated members. This enables rapid progression of the development on the schedule initially programmed. Clients looking for a rapid build tend to prefer this option as there is more certainty in the program schedule.